All right, so in this video, we are going to be talking about waves on a string and more specifically, standing waves on a string. Now, just as a quick note, a full wave will look like this, and that's going to become important to us here in just a little bit, but just remember a full wave will look something like that. Now, if I'm talking about waves on a string, we're going to start talking about harmonics and how a wave on a string looks when you're doing the first harmonic, second harmonic, third harmonic, and things like that. Now, the first harmonic for a wave on a string, so this will be the first harmonic, so the first one right there. The string is going to have a fixed barrier on both ends, like so. And the first harmonic is the lowest frequency that the string can resonate at naturally. And now what that's going to look like is a string like this, where it's something like that. It may not be the best drawing ever, but let me just change colors here. And then it's going to oscillate down to this right here. So it's going to bounce up and down between these two lines. Go back to my black. There we go. So the first harmonic is going to look like this on a string. It's going to just have one crest, and then whenever it oscillates, it's just going to have one trough. It's going to have a node here at the ends, nodes, and there's going to be one antinode in the middle. Now, this is going to have the fundamental frequency. So like I said, this is the lowest frequency that this string can resonate at naturally. Now, we need to also figure out what the wavelength of this is. Now, if I were to imagine this black line right here continuing on over here, it would end up looking like a complete wave, and it would look like this. Where you got it starts at equilibrium, crest, goes past equilibrium, trough, and meets back at equilibrium again. That's what one whole wave looks like. That would be a whole wave right here. It's kind of ugly, but that's what a whole wave would look like. So the length of the string is only half of a wavelength. So we could say the wavelength is equal to 2 times the length of the string, because you would need the string to be twice as long to create one wavelength. All right, so I'm going to leave that right there. Let's go and make a smaller line here, because we're going to move on to the second harmonic, and all the other harmonics are going to be built around this fundamental frequency of the first harmonic of a wave on a string. So let's go to the second harmonic, and we're going to have the same string with the same length right here. And it's the second harmonic is basically going to have 2 fundamental frequencies crammed into this space. So let's see if I can do that, where I draw the fundamental frequency once, and it's going to have the fundamental frequency again in here, like so. And the it's going to oscillate back and forth right here, like where it goes up, and then it's going to come back down like so. So this is what the second harmonic would look like for a wave on a string. It's got 2 fundamental frequencies crammed in there. Now these fundamental frequencies are supposed to be the same size. Disregard my terrible ability to draw these. But the second harmonic is going to have a frequency of 2f, 2 times the fundamental frequency, and the wavelength is going to end up being the same as the length of the string, because you notice this solid line here, it goes up and comes back down, and it completes one wave. So there you go. You have the second harmonic, it's twice the fundamental frequency, and the wavelength is going to be the length of the string. All right, so let's do the third harmonic now. Here we go, third harmonic, same length of the string, but now instead of having 2 fundamental frequencies, it's going to have 3 fundamental frequencies crammed into here. So let's see here. This is always a struggle to draw. See if I can get it where you got the first or one of the harmonics right there, and then you got another harmonic right here, and then you got the third one right there. So there we go. We got 3 fundamental frequencies put into the length of the string, and it's going to oscillate back and forth like so. So the third harmonic is going to be 3 times the fundamental frequency. So the frequency of this is 3 times greater than what the fundamental frequency was. And also you notice that the wavelength it ends up going to about right here. So if you start from there and go to this line that I drew right here, that completes one wave. But you still got another section of the wave over here, right? So we can say the wavelength is going to end up being 2/3 the length of the string. So it's 2/3 the length of the string, because you got a 1/3 right here for the first harmonic, another third for the second harmonic, and then a third for the third harmonic. But the wavelength is completed when you hit the end of the second harmonic right here. So this ends up being 2/3 the length of the string. Let's go to the fourth harmonic. So here we go, fourth harmonic, same length of the string. And you might be getting the process here. Now we're going to have 4 fundamental frequencies crammed in here. So let's see if we could do this. It always gets a little harder the higher the fundamental frequency is to draw. So let's see here, we got one fundamental frequency right here, a half wavelength. We have a second one right here. And then we got a third one right here. And then a fourth one right here. Oh man, that looks terrible. But you get the point. We got 1, 2, 3, 4 of the fundamental frequencies crammed in here. And like I said, these should all be the same length, but I'm just not drawing it very well. And then it's going to oscillate back and forth like so. And so this would be 4 times the frequency of the fundamental frequency. So the frequency is 4 times higher than what it was at the fundamental. And you also notice that we complete one wavelength when we are halfway through the length of the string. So the wavelength is going to be 1/2 the length of the string. Let's go down here. Let's do the fifth one. Oh man, this one's going to be difficult. All right, so we got the fifth harmonic. And what we're doing here, 5 fundamental frequencies are going to be crammed into this length of the string. Let's see if I can do this well. All right, so we got 1, 2, 3, 4, 5. All right, so we have the fifth harmonic right here, where it's going to oscillate back and forth between these 2 lines. All right, let's get all this done. And all right, so this wave is going to oscillate back and forth. So this frequency is 5 times the fundamental frequency. And also you notice that we complete one wave when we are 2/5 of the way through the string. So the wavelength is going to be equal to 2/5 the length of the string. All right, so those are the first 5 harmonics for a string. You could follow the same process to the 6th, 7th, 100th harmonic if you wanted to. The same process applies. The 10th harmonic would have 10 fundamental frequencies crammed into the length of the string. The frequency is going to be 10 times greater, and then you could figure out the wavelength from there. So what would that be? It would be 2/10 the length of the string, which reduces down to 1/5 if you want to do that for mental math. Now, why would we want to be knowing this? Why would we do this? So let's say that we have a string here, and let's say it's 2 meters long, 2 meter long string. So L equals 2 meters. And let's say we make the third harmonic on this. Let's see if I can draw the third harmonic. 1, 2, 3. And you know what? I'm going to make this a little shorter right here just to make sure. Ooh, that looks terrible. Just to make sure. I'm not making it look any better. Whatever. Just to make sure that we have this. I was trying to make this look great. Now it looks ugly. All right, so let's say we created the third harmonic on our string. So we got the third harmonic here. And the length of the string is 2 meters long. And let's say that it is oscillating at a frequency of 93 hertz. Okay? So I'm going to have 2 questions for you. My first question will be, what is the velocity of the wave traveling through the string? So how fast is the wave traveling through the string? And my second question will be the fundamental frequency. What is the fundamental frequency? Fundamental frequency. Or I could also say the first harmonic. So those are the 2 questions that I'm asking. Let's do the velocity of the string first. So we would end up using our equation. The velocity of a wave ends up equaling wavelength times frequency. And this is pretty nice because our frequency is given to us, but we're not given wavelength. Now, that's fine because we are given the length of the string. And we know the wavelength on the third harmonic is given to us right here, where the wavelength is 2/3 the length of the string. So I could just rewrite my equation where I say velocity is equal to 2/3 the length of the string times the frequency. All right, so that's pretty simple. And then we could just plug in our numbers. Let's see here. So the velocity is going to be equal to 2/3 times the length of the string, which is 2, and times the fundamental frequency, which is 93. Now, if you want to go ahead and pull out your calculators and figure out what this is exactly, you can do that. But I have already solved this. And if you want to go check my math, you're more than welcome to. But the velocity of this wave on a string will be 124 meters per second. So that's how fast the wave is traveling through this particular string right here. And so basically what we did is we were able to substitute our equation over here because we knew the length of the string, we knew which harmonic was being produced. We could substitute this wavelength for this part of the equation and then solve for what we have. Now the fundamental frequency, let's solve for that. Well, we look at this and we say, well, this is 3 times the fundamental frequency. So the fundamental frequency should be 1/3 of this. So the fundamental frequency should just simply be 93 divided by 3 because it's going to be 1/3 of the third harmonic, the fundamental frequency will be. And whenever you do that, you find out that you have 31 hertz as your fundamental frequency for this string. So there you go. That is how you can talk about standing waves on a string using harmonics and a little sample problems as to what you can solve for.